Yeah, that'd be
Okay.
great.
Yeah. Okay.
Thanks.
Yeah.
So let me just go ahead and start. So, hi, I am Archana. I'm the leadership fellow for the Python and the Cloud track with Brief, and I also I'm also working with Soham on this webinar series or the study group to help get the word out there about edge computing. And I'm basically I work as an AI engineer by day at Continental. So I work with using edge computing applications to the automotive industry. And we also have Soham joining in. So Soham is a machine learning engineer at Sleek, and he has created two Udacity courses, one on Intel Edge AI for IoT developers with me, and he also has developed one for Microsoft Azure for ML DevOps. And after that, he has worked. His master thesis was around neuromorphic chips, and now he's now working with Sleek for automating their pipeline. And very, very happy to have you, Soham, with us, and very much thrilled to take this forward. And so let's just start by quickly by our mission and vision. So as Women Who Code, our mission is to inspire women to excel in technology careers. Our vision is to have a world where women are representatives, not only as software engineers, but also as VCs, executives, board members, etc. Our target audience is usually people who are looking for 2 or more years of experience to strengthen and influence their and level up their careers. But we are open to all beginner level too. But we specifically want to target this because we believe that this is where women in tech need the most resources at this point in their career. And we have a very strict code of conduct, which means that we do not discriminate, regardless of gender identity, political affiliation, or preferred programming language, and so on. And if you find someone who's violating the code of conduct, feel free to fill this incident report form over here. And which brings me to all our upcoming events too that is happening. So just in case you want to check out some other events that the Python track is doing, we have like two series running in parallel to this. We have one on data structures with Python. We also have one with databases with Python. And let me go ahead and get started and hand it over to Soham.
Yeah. Thank you. Thank you for the really nice introduction. Um, yeah. Let me just start sharing my screen. So yeah, you should be able to see my screen now, right?
Yeah, I can see it.
Okay, awesome. Thank you. So yeah, so in the last session, if you remember, we just tried to give you like an introduction to what edge computing is, why it is important, and why the field has been growing so quickly recently. But now we want to kind of dive in a bit deeper, and we want to see like what are the basics of running neural networks at the edge. What are some of the key metrics and considerations that you need to take into account when you decide to deploy a model in an edge computing device like a microcontroller or a microprocessor? Um, so what we'll be talking about today first is we'll do like a recap of the last week. So just so you know, if you hadn't joined last week or if you don't remember, we'll just do a short recap. Then the key thing that we'll be looking at today is how do you measure your performance at the edge? And what are the key performance metrics that you need to take into account when you deploy a model at the edge? We'll also talk a bit about how you can measure these metrics and then how you can optimize for certain metrics. So it's not not all applications need to be fast, or not all applications need to be optimized for all the metrics that we have for edge. In some cases, as long as you're very good at a few things, that's more than good enough for you to go ahead and deploy it. So how do you know which metrics to optimize for? That is what also something else that we'll be covering. And finally, like I mentioned before, this is a study group. This is not like a talk or a workshop. So you will have homework that you have to, like go back and do it. Don't worry, we have a Python Slack. Sorry, we have an edge computing Slack group. And both me and Archana are really active on that Slack group. We try to post links, links to papers, projects, key people to follow in the field. And if you are someone who is facing trouble with doing the homework or something, feel free to like join our Slack group, and we'll be more than happy to help you. um, yeah, also before I go ahead, I wanted to show you the roadmap of our study group. So today we are doing this second session. From the next session, we'll be doing a lot more hands-on, and we'll be actually trying to quantize a neural network so that we can run it on the edge device. So we'll see, how quantizing the network affect your will affect how uh, so we'll see how quantizing your network will affect the accuracy of your network, but at the same time, we'll see how quantizing it will actually make your network run faster. And yeah, and then we'll be moving on to like my favorite topic, which is like hardware at the edge. And we'll be seeing like what are the different hardwares and how do you actually use those hardwares at the edge. And yeah, we'll also be talking about research. We'll be seeing some other algorithms like pruning. And finally, we hope to kind of like do like a mini project as well. So yeah, so let's go and look at our a recap. So if you remember last time, what we talked about was the number of IoT devices that are out there in the world connecting to the internet is actually increasing really quickly. And this year, the number of IoT devices is actually kind of like is equal to the number of non-IoT devices. But pretty soon that's going to change, and we'll have a lot more IoT devices than non-IoT devices. And so what this means is that these IoT devices, which have a lot of sensors and they collect a lot of data, they'll all of this data that the sensors are collecting, chances are that they won't actually be used at all, right? So McKinsey actually found out that more than 99% of IoT sensor data is actually like discarded. So think of it in this way, right? If you have a smart refrigerator, right, or let's say like a smart I don't know, smart toaster or something. These are things that will be recording stuff like the temperature. So a fridge might be recording the temperature, and so might a toaster. They'll also be probably monitoring the power consumption, and also, so these devices have sensors to do all of this. But that data is mostly not used. But you can actually use that data to perform things like predictive maintenance. So, if a model sees that the refrigerator temperature isn't rising as fast as it should, um, isn't rising as fast as it should, it will most probably, you can do some predictive maintenance and send someone to fix that fridge. Um, and that is basically what the power of IoT is, and all the sensor data is. But it's kind of not really possible to send all of this data to a cloud server and then do some calculation on it, because like a lot of these devices will generate a lot of data. So for instance, a security camera might be generating like gigabytes of data every hour, and most people don't really have the internet bandwidth or the speed to actually send that data to an internet source fast enough to so that you can analyze it. So what do you do in such a case? So you try to actually deploy your edge computing models closer to where your data is being generated, so at the device itself. And the advantage of that is that you don't have to send data over the internet. You don't have to there's no latency, because since you're not sending data over the internet, there's no latency, and like I said, reduced internet bandwidth and increased security as well. So because you're not sending data anywhere, there's no possibility of an attack, like a man in the middle attack, where someone actually sees the kind of data that you're sending, and that data might actually be really sensitive, like for instance, if you have a security camera, right? And finally, you have a reduction in dependence on cloud services. But despite all of these advantages, there are actually a few problems of running algorithms at the edge. One of the biggest problems is power constraints. So because most of the microcontrollers we have are really simple, really tiny devices that run on, maybe a few watts of power, like, I don't know, 10 watts, 15 watts. These are not really meant to perform really powerful calculations, right? They don't have they're not as powerful as your standard laptop CPU or GPU. So power is a huge constraint. Also, many of these systems might be running on a battery, right? And if you have a neural network running on that system that is, like consuming a lot of power because you're doing a lot of calculations, your battery might run out really quickly. So power is something that we need to keep in mind when we deploy something at the edge. Another really important thing is the floating. So this is not something a lot of people are familiar with, but when you like do a calculation on your laptop, right? You're not working with integers actually. You're working with floating point values, and floating point values are values that are um, so they take like 32 bits to represent a single floating point value, and because we use so many bits, right, to represent these numbers, we can get really high precision, and we can also get a really large range of numbers that we can represent. But turns out, like, because of that, because there's like so many bits that you need to take care of, it's really hard to work on floating point numbers, and it's really slow. Like computers like are really slow, and CPUs in general are really slow when they try to do floating point calculations, which is why most CPUs, GPUs, like most devices that we use commonly, they actually have like special hardware inside them that actually perform these floating point calculations. Um, so one thing you can actually do to see like some of the disadvantages of using floating point is go to your Python interpreter, like open up IPython or something, and do 0 0.1 plus 0 0.2, and see the result. I think you'll be really surprised if you see the result. And like we can discuss in the chat later on the result you get and why you got it. But yeah, coming back to my point, most microcontrollers and microprocessors, they don't have this special hardware to perform floating point calculations because they don't need it. And so neural networks, we have to, even though floating point numbers, they give us a lot of accuracy. When it comes to deploying it on an edge device, it's like you really can't use it. You have to convert your network into like an integer format or something. Um, yeah, another thing is memory constraints. So our laptops, our GPUs and all, they have like a huge amount of RAM. 4 GB is like kind of like a standard in most laptops, and even most phones actually. GPUs have even more memory, like, I don't know, 12, 16 GB probably. But a microcontroller or a microprocessor like a Raspberry Pi has just like 1/4 of that amount of memory. So you can't really load large networks onto it. So you need to also like reduce the size of your network. If you're going for like even smaller devices, like let's say an Arduino, you can't even save a really large model because it only has like a few megabytes of memory, like let alone like loading it into your RAM. You can't even store it on your storage on the onboard storage in your Arduino. So we need to find a way to kind of reduce the size of our model. And finally, inference efficiency. So our CPUs, our laptops, cloud servers, they can run these neural networks really fast. And if they're not running it fast enough, you can easily add two more CPUs or another GPU, and then eventually it'll run really quickly. But that's not the case when you try to run something on a microcontroller, because you know um, they don't have a lot of these very efficient CPUs and GPUs on them. But at the same time, we can't have the inference happen slowly. So inference, for anyone who doesn't know, is it's how fast the model is being executed. So how fast is the time it takes to from when you send an input to the model to when you get an output. And if your device is not very powerful, it'll take a long time to do that, and that kind of defeats the purpose, right? Because you don't want you want to get rid of your internet lag and all of that, but in case But if your device is so small and it's executing networks so slowly that it's taking more time than it would take to send your data to a server, then it doesn't really make sense to use edge computing. So we need to infer our outputs really efficiently and quickly as well.
Hi,
Right.
so we
Yeah, sorry,
actually
go
have
ahead.
someone raising up their hand, and I would love
Yeah,
to
sure.
invite this person to come talk. Hi,
Sure.
Sheshu.
Yeah.
Yeah, I think you did already. Um, did you raise up your hand, or we have another guest raising up? Okay, yes, you did. So shall I just invite you to talk? Let me just go ahead and do that. Okay. Um, yeah. So I just invited you to talk.
Yeah, no, I'm good. I just got my question clarified anyway. So yeah, I'm good. Thank you.
Okay. 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 Great. Great. So yeah, you could let us know if you want to come up and talk. We can allow for that to happen.
Yeah, just
Okay.
raise your hand and we'll invite you to talk. And I think at the end of this session, we'll also like invite everyone to talk so that we can have a really nice discussion. Um, yeah. So okay. So I've been talking for a long time, and but basically what I've been meaning to say is like the edge computing is really cool, but there's also a lot of problems, and we need to have some goals in mind when we try to optimize our edge computing system. So the first thing is our model should load fast, right? So if you try to load a model on your PC or your laptop or something, you'll see that it takes some time to read the model from memory and then put it in your RAM. And it can take anywhere from a few seconds to maybe even a minute, depending on how fast or how slow your laptop is. Um, so in an edge computing system, especially something that has to be stopped and started frequently, you might have systems like that. It's important that your model loads really quickly. You don't want to wait like 60 seconds for your model to load and then and then it starts predicting, because something might have had already happened in those 60 seconds. So for instance, one example I can think of is, say, like a self-driving car, where if you switch it off, your none of your devices, none of your onboard computers are getting any power. And then when you start it, you want your model to be loaded and you want it to be ready for performing inference as soon as you press the accelerator, like right after starting your car. So yeah, model should load really quickly. Also, like less space should be required to store the model itself. This is because most edge computing systems don't have a lot of space. Memory actually takes up a lot of power. So just fetching like memory from like say an SD card or something, it takes up a lot of power. So if your model is smaller, it'll require less power to load the model, and it'll also require less space. Fine, and one of the ways to kind of make your model smaller is to make it have fewer parameters. So like basically, like, don't train a network with like 10 layers and 100 neurons in each layer. Train a smaller network. Chances are it'll be fine, it'll work equally as well. um, and yeah, this is kind of similar to the first statement, where your model should kind of compile really quickly as well. So once it loads into the memory, it should be initialized. The graph should be kind of embedded into the memory quickly enough, so it should be compiled fast enough so that you're like you can start making predictions really quickly. And the last thing is accuracy. So now you might kind of be wondering, like, why did I put accuracy at the end? Isn't accuracy like the most important thing in an edge computing, in any machine learning system? And you're right, but the paradigm kind of changes when you come to to an edge computing system, because um, when you try to optimize, and we'll see this later on, when you try to optimize for some of these other parameters, what happens is you have to make changes to your model, and those changes will more often than not reduce the accuracy of your model. um, and as someone who's trying to start working in edge computing, this might seem like really bad. You might think that like, I'm doing all of this work, but at the end of the day my accuracy is decreasing. And basically you can't, that's not the right thing, that's not the right way to think about it. because accuracy it's important, yes, but at the same time in edge computing you'll find that it's more important that our model executes faster, even if you lose like say 5% of accuracy. um, and I know that sounds weird, but that's something that you have to kind of like adjust to and like take as like written in stone or something. It's okay if your accuracy is lesser as long as your model runs faster and loads faster. um, right? And we'll come back to this point in more detail later on. But basically, from those previous goals, there are three key metrics that we need to think of while we deploy a model at the edge. The first one is inference time. So inference time should be as low as possible so that we can run more model. We can run our our inference quicker. And we'll see different ways that inference time can be measured, and different ways in we can optimize for inference time depending on your application. Another thing is model size. So yeah, smaller models, like I said, takes less time to load because there's less memory that needs to be transferred. It also takes less energy to load, and it takes less space to store. Um, Finally, like I said, accuracy, it should be as high as you can get it, but it should not be, accuracy should be the last thing you should think of. And even if your accuracy is high, it should not be at the cost of some of the other metrics. Okay, so now I know like, you're listening to me and thinking like, okay, like what the hell is wrong like with you? Why are you saying that accuracy is not important? So that's the thing that I wanted to talk about first. And what I want to say is accuracy is important, but there are different ways that you can kind of shift the problem so that accuracy is does or you there are different ways in which you can measure how well your model is performing on your test data. And one of them is actually plotting this, like seeing your true negatives, false positives, and so on, and using that to get a measure of how well your system is performing. So let's say we have like a very simple example, like you want to detect whether an animal, like say you have a camera trap in the wild and you want to see if an animal is present in the frame, right? You want to track the number of animals in a given location, let's say. Um, so in such a case, a true positive, which is what we want, is kind of like, is in if in actual there is an animal present in the frame, and the model detects it as so, like there is an animal. But a false negative, on the other hand, is when an animal is actually present in a frame, but the model does not detect it. Um, so you can see that in such a case that having it's really important that we don't actually have a lot of false negatives, but it's kind of like um, um, it's fine if we have like a lot of false positives, right? It's fine if there are a lot of frames where even though there is not an animal, our model detects like there is an animal in the frame. It's fine if we have if it's fine if you have a model that does that a lot, as long as it doesn't give a lot of false negatives. Because at the end of the day, you can have a human later on kind of look at all the frames and then check if there's any false positives, but there's no way to kind of handle a false negative if your model doesn't actually detect it, right? um, so how do you actually measure this? So we can measure this with something called precision and recall, right? So recall is actually the ratio of true positives to the sum of your true positive and false negative, right? So this is something that in like a animal detection system that you want to optimize for. Even if your accuracy is really high, sorry, even if your accuracy is really low, it's actually possible to have a model that has really high recall. Um, and so, accuracy might actually not be that important in that case, as long as you have a really high recall. There's also this other thing called precision, which is the ratio of true positives to true positives and false positives, right? And when would you when would you want to kind of optimize for something like this? So for instance, in an ad recommendation system, the cost of like, not the cost of giving like someone a false negative is actually less than giving someone a false positive, right? For instance, in an ad recommendation system, you have like these huge servers trying to figure out um, which ads to send me, and if the system keeps sending me like ads that I'm not really interested in, like things that I might not buy, then that's going to harm the system more than having false negatives. So that's when you want to you may want to optimize for something else. Um, but I'm talking about all of this, but how do we actually bring this, like put this into practice? So in the animal detection case, right, you in your edge computing system, you might have like a cascade of models, and this is actually a very common way to deploy models in edge computing systems, where you have a very small model at first that's doing like a very simple task, right? A task of, say, just detecting if an animal is in the frame or not. And this can be like a really small model with a really high, false positive rate. And that's fine, because we want to capture as many of the animals as we can. And only if an animal is present do we send the image to a larger model to classify which animal, right? And this larger model, depending on your use case, it can be present in the cloud, or it can be present on device as well. But as long as we are running the larger model for fewer number of times, we are in the green, because our goal is to reduce the size of our model. And if we have a small model running most of the time and then a large model running sometimes, then that's great. Um, yeah, another thing that we need to consider when we deploy a model at the edge is latency. So latency is how long it takes for a model to kind of perform a prediction on a single input, right? So how do we measure latency? So it's one image at a time, like I said. So let's say we have a system that takes 1 second to perform inference, right? So this means that from the time an image is available to our model to the time that we get our output, it takes 1 second. So our latency in this case is 1 second. Um, so how do we know how many predictions we're making per minute then? So we can multiply latency to the time, right? So let's say if we're taking a minute, so 1 into 60, and so that gives us 60 frames per minute. So when you talk about like this metric, like frames per minute, we're talking about throughput. Throughput is how many images that we can send through the network in some time. So in our case, let's consider a minute, right? And yeah, so 60 frames per minute is 1 frames per second. But basically, what I want you to take away from this is latency is inversely proportional to throughput. Um, and so what this means is, in your system, you can optimize for only one of these things. You can either have really, really high latency, or you can have a really, really high throughput, but very low latency. Um, and I think it's easier to see this when we do like some calculation. So let's take a look at a model with like high throughput. Um, so so our hardware or our software framework, it can be optimized to perform um, inferences on multiple images at the same time. So let's say we have a system that performs that performs calculations on 5 images at a time. And let's say because we're performing calculation on 5 images instead of one, it takes more time to perform that calculation, right? So let's say it takes 2 seconds. So our latency will be 2 seconds, because it doesn't matter if your 5 images are available like instantly, or or if each image takes like 1 minute to come. the minimum latency that you will have is 2 seconds. You'll also have another latency associated with with a system like this, which is, if images take a longer time to arrive. So for instance, maybe you have a camera that's taking like 1 image per second. So you'll need at least 5 seconds to capture 5 images to perform inference. So that's also another latency, but we'll not consider that for now. So predictions per minute in this case, it'll be, because we're doing 5 at a time, 5 divided by the time it takes to do one prediction, so 2 seconds. So that's like 150 frames per minute, which is actually quite high, right? It's 2.5 frames per second. And so you can see that even though our latency has actually increased 2 times, our throughput has actually also increased, and it's increased much more. It's increased 2.5 times. So latency, so we can like kind of edit this formula and add batch size here. And this is kind of our correlation between, a relation between latency and throughput. So what is a system that kind of where we'll need like low latency but high throughput, and vice versa? So latency is when you want to quickly process like each data as soon as it arrives, and this is important in like in a system like a self-driving car, where you don't want to wait for further images to arrive, right? You, as soon as you get an image, you want to perform inference, because if you delay your inference performing, like if you delay how fast inference is being performed, um, that can lead to an accident or something. So in a self-driving car, you will want to optimize for latency. You'll want to optimize for throughput in like in cases where you have to process like a huge amount of data together. So for instance, you could have like a traffic light monitoring system, a traffic monitoring system. And, in a system like that, you could have like, in a large junction, you could have like, I don't know, 8, 10 cameras, and maybe just one microcontroller processing all of the inputs from those cameras. So in such a case, you want to be able to really, really quickly go through all of those images, right? And so that is a case where you might want high throughput, where you want to process like a large volume of data from multiple sources at a single point. Okay, so
Yeah.
next, yeah, sorry, go
Before
ahead.
we go ahead, yeah, I just want to take some moment out here because we have given quite a bit of information. Just in case you have any questions for us, do drop it in. And I was also wondering because, would you like in some ways consider throughput or latency to be equivalent to accuracy in the deep learning world in some ways? Because, I have been working on projects last year, and wherein like for me, FPS was really important because we were dealing with a multiple camera setup. And, my, like basically my team was behind having a high FPS always.
Right.
Like you can process more frames per minute or frames per second. It's greater and it's better for us in the long run. And, we used to always have this differentiation of devices. So for example, we had like smaller devices, for example, Jetson Nanos, and we were also working on the Jetson AJX. And obviously we noticed that the Jetson AJX, which is much more powerful than the Nano, having like a higher FPS than the Nano. So, but long story short, what I want to say is that do you think in some ways we are moving towards having like a FPS go-to scenario for
Right, right.
or a latency based scenario for a edge computing world?
Yeah. Yeah. So that's a really question. That's a really good question, and this is where I want to also reiterate the point of accuracy not being as important in edge computing. So let's say like you have like I previously mentioned, a traffic light monitoring system. So this system could have like, let's say, like a 99% accuracy. Oh, sorry. So let's say it has like 99% accuracy, but it takes 1 second to perform like the batch inference, right? So what this means is that if your images are being captured, like let's say at a rate of all of your images are being captured every half a second, then that means your system, even though it's really highly accurate, it'll keep lagging by half a second. And in a case like a traffic light monitoring system, that half a second can be a lot, right? That can be a difference between an accident happening, or maybe and those half seconds will keep building up, right? After 2 seconds, the difference will actually be 1 second, and that will keep building up. So, and that could mean the difference of, let's say, like an ambulance waiting for 1 extra minute at a traffic light, because the system hasn't spotted that ambulance, and it hasn't stopped all of the traffic lights to let the ambulance go. That could help save a life. So yeah, in such a case, as long as your system is really fast, it's more important that your system is really, really fast, than it is a highly accurate. So you may optimize your model, and you may optimize your system, so that your FPS is similar or lower than the time it takes to capture images, at the cost of, let's say, like 10% of your accuracy. So now your accuracy is 90% instead of 99%. um, and in most cases that is actually good enough. um, and good enough is what we're looking for, because what we need to be really, really good is our frames per second, and how fast we are performing inference in an edge computing system. So yeah, I hope that
Yeah,
answers your question.
absolutely.
Yeah. So
Yeah,
I see
it
we have
does. So
like
we
some
actually have a few
questions. Yeah.
questions. Yeah. So I guess one of the Kuldul is actually asking about repeating latency and throughput. So could you do that? Because I know this sort of term is such is like quite new, especially in the deep learning scenario, because as Kuldul even pointed out, this is the first time he's hearing it, which is very
Yeah.
true for most of us out here. And what we need to understand is that this is like one of the metrics that's bound to come up eventually. I believe that we are moving towards a world where accuracy is like accuracy is going to be it's not going to be the go-to standard anymore, because we're going to have models which are really, really accurate now. You will find every other day another model having, if a model has 97% accuracy, you're going to have another model which is going to be like 99 accuracy, right? And we're going to keep moving towards having models which are like really great in accuracy. But I think down the line these metrics will matter more. So could we also repeat it if possible?
Yeah, sure. Maybe we can do it at the end, so that like we cover some of the other.
Sure.
Yeah. Okay. Great.
Yeah, absolutely. Yeah, okay.
Yeah. Are there any other questions? Like, because I know we covered like a lot of really like.
Yep.
Yeah.
True. So we have, is it possible to have more than one model on the edge device?
Oh yeah, for
also
sure.
like add, yeah. And
Yeah.
they're also asking, also add logic on the edge device to pick a smaller model, then pick a larger model if the smaller model is giving true positive results.
Yeah, exactly. And that is a really common scenario in a lot of edge computing systems. So then this is what I wanted to show here as well. So in a case like this, we have a smaller model that we run like a lot of times. And because it's a smaller model, it's not consuming a lot of power. It's not, it's not taking a lot of time to perform inference. It has really high throughput or really low latency. And as soon as this smaller model detects something that is useful, it can send that same image to a larger model. And so the larger model, it's more accurate, right? And because it's larger, but because it's larger, it's also taking a lot of time to perform that inference. So yeah, this is a very common system where you have two models uh, deployed in the same edge device. And we have a smaller model that's acting like um, that's just acting like a gate that opens up to the larger model only when the smaller model sees something that's interesting. That's a very common scenario, and yes, it is possible.
We also have another question, which is about what are some good books to read about edge computing and something related to
Oh,
deep
right.
learning and ML?
Yeah. So yeah, maybe we can share some of the books in our Slack group. Like I can think of a few.
Yeah, we have the
Yeah.
TinyML
Yeah.
book. I can share that, and some. So we also have like a Harvard course. Is it the one that you were
Yes.
doing before? It was a Harvard-based course, right?
Yeah.
So I
So
can
there's a
also share
course.
that.
Yeah. Sorry, go ahead.
Yeah. No. I just have those two in mind. You have
Oh,
more?
yeah. Yeah, the TinyML book by this guy called Pete Worden, who is one of like the founders of our field. That's a really great book. There's also a course on edX called TinyML. That's also a really great course. Um, Apart from that, mm, I don't think there are any books per se, but there are a lot of blogs that I can ask you to read. And I think it's also important to have like a bit of electronics background, because since we'll be dealing with hardware. So maybe read a book on like basics of electronics. And I can say I know one really good book, but I can't remember the name right now. Maybe I'll post it in the Slack group or in the chat after this session. Okay. Are there any other questions, Archana, or can we like move on?
I think we can move on. We just have one more. Can the larger module be in the same network as the small network, as a smaller network?
Oh yeah, for sure. And yeah, and you've kind of like brought about like a really important point, which is and a very important area of research right now, and we'll be covering it as well later on. So that's called early exits. So what happens is you have like a really large model, but usually when you have a really large model, you send an input and then you get the output at the end. But what if you can get outputs at intermediate locations of the model? So that way you don't have to run like a huge model. You can only run like this much of it, and it's faster and it's smaller, and get an output. So yeah, you can have like a situation like that as well. Yeah. It's called early exits, and we'll be covering it like I think in session 6 or something. Yeah. Okay. So I think we're running a bit short on time, so I just want to like quickly go through these things. Um, there's this thing called flop and Mac. So when you when a new CPU or a new computer is released, you might see Intel say something like, "Hey, our new CPU can do like I don't know 10 gigaflops of operations." What this means is like it can perform 10 giga floating point operations per second. So I mentioned before, right, like how it's difficult to perform floating point operations because they're very complex and they are and most CPUs are not really optimized to do it. Um, so in such a case, you know, you want to measure the number of floating point operations that your model has and try to reduce that. That's a really good metric to optimize your model for, because it tells you how big and how complicated, like computationally complicated, your model is. And if you can reduce the number of floating point operations, then then you know that you're moving in the right direction to kind of make your model run faster. So one way to actually measure, so floating point operations is actually not something that the hardware does. The hardware does an operation called a MAC. And MAC is the short form of multiply and accumulate. And a MAC operation is basically you do a multiplication and then an addition. And this is the most common operation that happens in any neural network. So if you remember, when you were learning about neural networks, you'll know that to execute any layer, we do weights, which is W, times X, which is our input, plus B. So we are doing WX, which is like a multiply, and we're doing also a plus B, which is an addition. So that's like the most common um, that's the most common operation that we do when running a neural network. And so your hardware needs to either be really, really optimized to do max, or your model has to have really, really fewer max, right? To make it run faster. And one mac, because it's kind of equivalent to doing two flops, because we're doing two floating point operations, right? A multiplication and an addition. So one mac is two flops. But in many hardware, like the Mac operation is kind of fused together. So hardware people are like really, really smart people, and they figured out how to do both together and like really fast. So yeah, that's why we have like a similar sign and not an equal to sign, because in many cases it's like one flop itself. Um, yeah, but how do we actually know that the number of max is lesser, and how do we calculate it? So it's actually really easy to calculate it for networks, and I want to show you how to calculate it for like a separable convolution. So separable convolution, if you don't know, is we divide a normal convolution operations into two parts: a depthwise convolution and a pointwise convolution. And people say that you do this because it reduces the number of operations, the number of weights is less, and so on and so forth. But no one actually tells you the calculation that actually shows you how it is less. So let's actually try to calculate that. um, and I know this is like this is a bit complicated, so feel free to like raise your hand or post a message in chat or something, and I'll be more than happy to explain this in more detail. But let's take a normal convolution at first, right? So let's say we have an input, an RGB image of, let's say it has 12 by 12 pixels, and because it's an RGB image, it has a depth of 3. Now let's say we are running a filter, right? A 5 by 5 filter. Now, because it's a 5 by 5, because our input has 3 dimensions, our filter will also have 3 dimensions, right? And our output shape will be 12 minus 5 plus 1. That's how you calculate your output shape in a standard convolution. So 12 minus 5 is 7, plus 1, that's 8. And let's say we do this 256 times. So we'll have 256 as our output depth, right? So how do you actually calculate the number of floating point operations or flops that have taken place when we try to execute this module, this layer? So it's actually this like really large, and it looks complicated, but it's not. It's really easy, right? So let's say our filter is at this position over here. So how many multiplications do we need to do? We need to do 5 multiplications on this side, 5 multiplications on this side. So that is our filter dimension. So D into D. And we need to do that for whatever is our depth over here. So 3. So that's our depth here, 3. Right? And then, right, like this filter will kind of move towards the right, and then it'll move down and so on. And how many times will it move towards the right, and how many times will it move down? Well, that's equal to the number of to our output shape. So it'll move 8 times on this side and 8 times on this side. And every time it moves, it has to do this calculation, right? Like these many calculations. So we then multiply with our output width and our output height of our image, and we need to do this whole thing 256 times. So we multiply with n, which is the number of output channels, and this is the number we get. And this is how many flops we have to perform to execute like a simple layer like this. So for this case, if we do the multiplication, so like let's do it. So it's like dk into dk, which is 5 into 5. Then we have w naught h naught, which is 8 into 8. Our output depth, our channel depth is 3, so 3. And this depth is 256, so 256. So a bit more than 1.2 million flops for this layer. Now let's see how we do it for a separable convolution. So in a separable convolution, we have the depthwise layer first. And this depth-wise, and we also have like a point-wise layer. So the total flops for the depth-wise is going to be similar to this formula here. So we're going to still have dk into c, because we're still doing the same calculation. And we'll also have the W naught and H naught, which is our output height and width. What we won't have is N, because in a depth-wise convolution, we only have one filter. We don't have like 256 or something. So our output shape is also going to be, our output depth is going to be equal to our input depth, right? And a point-wise convolution is similar to a normal convolution itself. Um, but the only difference is our kernel only has a shape of 1 by 1. So it's going to be this formula, but we can remove dk and dk because dk and dk are both 1 and 1 into 1 is 1. So we can forget that part. And so our total comes out to be this. And you might think that this looks larger than this, but in reality, it's actually not. And if we divide both of them, we can see that we get a savings of this much, right? We get a savings of 1 by n, because we aren't multiplying by n over here, and we get a savings of dk square in the pointwise, because our convolution shape is 1 by 1. And so our total flops in this case is only a bit less than 54,000, which is actually 22 times lesser than this. And so this means that you can run, your latency can be 22 times more, because you're doing 22 times fewer calculations. Or you can do parallelly like 22 more. You can run this same network 22 more times parallelly. And the cool thing about this is our input and output shapes actually remain the same. So here we have an input of 12 by 12 by 3, same here, and our output is 8 by 8 by 256, which is the same here as well, right? So we are reducing the number of parameters, and we're also reducing the number of flops it takes to execute this network. So I know this whole thing was like super complicated and really confusing, and I felt it, and when I tried to learn it, it was the same for me as well. So don't be discouraged if you don't understand it at first. We'll share the slides, we'll share this video, and you can watch it later on as well. And feel free to reach out to us as well.
Yeah, so we actually have someone asking a question if you have
Sure.
some time.
Yeah.
Kuldul is asking why is it DK 8 why? So I was wondering if Kuldul will be open to coming up and asking too, just in case he has like some more questions around it. But yeah, sure, you can answer why is it DK and 8. Yeah, I mean, you can answer that for now until like if he wants, like he can come up and ask.
Sure, yeah. So is the question, why are we multiplying with dk?
Yeah, I think Kuldul raised his hand. Let me just allow him to speak.
Yeah, sure.
Yeah. Hi, Kuldul. I think you're allowed to speak now, like you can.
Yeah, hi. Thank you. Regarding dk, my question is why k is equal to 8 here? Dk is equal to 8. Because here total. Yeah.
Right. I'm really sorry. Dk is not equal to 8. I kind of flipped this around. Dk is actually equal to 5. 8 by 8 is our output shape. It's W naught into H naught. And like my fault completely, I understand why you're confused. This thing should be at the end, and 5 by 5 should be in the front.
Okay, so 8 it's weight. Yeah, 8 is weight and height, and 5 means decay here.
Yeah, exactly.
Our case.
Yeah.
Okay, and 3 is input. Yeah, okay, I get it. Thank you.
Yeah, no worries. Yeah, really sorry about that.
Thank you.
Yeah. Are there any other questions, Archana?
No, but guys, this is, as Soham said, something which is a little complicated, and I know a little math heavy, or might seem a little math heavy. So feel free to ask us any questions at any time.
Mm-hmm. Yeah, absolutely. Yeah. So finally, we talked about the really, really huge, complicated metrics. We talked about accuracy, precision, and recall. We talked about latency and throughput, and we also talked about flops and max. There are also a few other metrics that I think you need to kind of think about when you're deploying a model at the edge. So one is system power. So for instance, your model can be deployed on a system that is battery powered or maybe powered using solar power or something. And in that case, you want your system to not consume a lot of power so that it runs longer, right? So you want to optimize for a longer operating time. And one way you can measure that is to see how much each component of your system is consuming. So for instance, like, let's say we have a PyCam, right? Like a Raspberry Pi with a PyCam, and we are running it off like a standard, like say 6,000 milliamp hour battery. Um, if you actually do the calculation for that, if you know, like homework, if you go back home and see how much power each of those things consume and then add them up, and then divide that with 6,000 milliamp hour, you'll see that that the device will only run for 1 day, right? And 6,000 milliamp hour is actually a really huge battery, and despite that, it'll just run for a day. Um, you'll want to optimize much more, like you'll want to use something more power efficient if you want to deploy something like that. Um, Another thing is system size. Not as important in a lot of cases, but say you're deploying something in a place where space is a constraint. So let's say you want to deploy something in a forest, and you want it to be really small, and so that, you know, animals don't see it and then get spooked or something. So you want it to be really small. So that's also something that you might want to optimize for. Or let's say you're deploying something in a factory floor where, you know, you don't have a lot of space, and each inch of space is like very carefully planned. So yeah, you might want something that is much smaller. And finally, system cost is also important. So if you're deploying like the wildlife example, if you're deploying multiple cameras in a really large forest, you'll want each system to cost really less so that you can deploy many of those systems. Yeah. So these are also some other metrics that I think you need to take into consideration. Oh yeah, another example for system power is, let's say you have a self-driving car, and you know that has a finite amount of battery, but you want your self-driving car neural network to run longer, so that, you know, your car can also run longer. So yeah, that's also where system power is really important. And yeah, finally, don't write bad code. Me and even Archana, we come from an electrical engineering background, and neither of us have any formal education in computer science. Like if you ask me to invert like a binary tree, like I don't even know what a binary tree is, honestly. So yeah, and I've never really made one, so I won't be able to do that. But what that also means is that I write really bad code, like not optimized code, because I haven't really learned all of those techniques or algorithms. So you'll also want to check the bottlenecks in your code. In general, what you'll find is like deep learning frameworks like TensorFlow Lite and so on, they are like super optimized, and so they might actually not be your bottleneck at all. It could be that your data loading and your data pre-processing is what the bottleneck is. So how do you actually find that out? So you can use like a line profiler that tells you how much time it takes to execute each line to make sure that there are no bottlenecks in your code. So this is like an output from a line profiler in Python. What the code does is really not that important, but just to give you like an overview. So we have this one line that loads the model into memory. Remember I said towards the start that even loading the model and compiling it might take a lot of time. So that is what is happening here. Then we have another function that is pre-processing the image. So it's reading an image and then pre-processing it. And then finally, we are performing inference on that image. Right? So if you see the percentage of time, you'll see that it actually like the time it takes to run inference is just 1.6%. Our pre-processing is actually taking a lot more time. And so in this case, optimizing your model, it doesn't really make sense. There's this really famous computer scientist called Donald Knuth, and he said premature optimization is the root of all evil. And this is a perfect example for that. If you prematurely start optimizing your inference, your network, you won't actually see any gains because most of your bottleneck is here and here as well. So this is what you want to first optimize for, to make sure that your pre-processing pipeline is really fast. So yeah, don't write bad code. Make sure you use a line profiler to actually check your code, because most of the time you might not even have to need it to optimize your model. Which brings me to the end. How do you optimize, and which metrics should you optimize for? So yeah, first make sure that you actually need to optimize, because optimizing, it takes time, it takes a lot of effort, and it takes a lot of time to actually perfect it, to get your model to a stage where you can say, yeah, my accuracy is great, my latency is also great, I can deploy this. That takes a lot of time, and most of the in many cases you might not have that much time. So make sure you know whether you actually have to optimize, and maybe you don't need to. Maybe you can just get a better developer who writes a better who writes better code to pre-process images. Maybe that's more than enough. And don't cut yourself short over there. That's also a form of optimization for edge computing. And it's equally, if not more important than performing inference. Yeah. So kind of like, in addition to the first point, it could be like there's a problem with your hardware or your framework. So maybe your hardware is not fast enough, or maybe your framework doesn't really support or is optimized for a particular hardware. So yeah, after you see whether optimization is required or not, make sure that your hardware and your framework matches, and it makes sense to use that hardware. There's like so many types of hardware out there that I'm sure like you'll find something or the other that suits your needs. Like, power might not be an issue in your case, and you can use a Raspberry Pi, which is, a bit more computationally powerful. But in other cases, power might be an issue, in which case using a Raspberry Pi doesn't make sense, because it also consumes a lot of power to do all those calculations. So in those cases, you might need to use, like, it might be better to use a Arduino or something. Yeah. There's also a lot of frameworks that are optimized for edge. So for instance, a framework like, I don't know, I'm just like saying, like, for instance, PyTorch, let's say. I don't think PyTorch has any edge. They have a lot of edge computing specific algorithms, but I don't think they're like optimized to be deployed on the edge. I could be completely wrong. I haven't done it, but just to give you an example. On the other hand, other frameworks like, let's say, TensorFlow Lite or Intel's OpenVINO, these are really optimized to run on the edge. And maybe shifting to another framework will improve your speed. Yeah, and another thing is, like, as we've seen before, right, with latency and throughput, oftentimes, and usually most of the times, optimizing for one metric can affect another metric. So quantizing your model to make it run faster will definitely affect your accuracy. So choose which metrics are important. You can't have a system that is very high throughput and very low latency, because as we saw, they're inversely related. So you should understand that optimizing something, to gain something, you'll have to lose something else. And because of that, you have to choose what to optimize for. So in a self-driving car, you might, like, depending on the application, like in a self-driving car, you might want to optimize for latency. In some other application, you might want to optimize for throughput. And a good way to see that is to see what the requirements are. And based on that, choose your hardware, choose the model, and choose which metrics that you want to optimize for. And finally, like, forget about accuracy. And I know for a lot of you this might seem really hard to do, but in general, accuracy is the last thing you should be thinking of when deploying to the edge. Yeah, so that's it.
Yeah.
So this is your homework. So your homework is read a research paper that compares, different networks, hardwares, and frameworks, and it compares the different metrics. So how do you actually find a paper? And many of you might not have experiences with reading papers, so you might not know how to find it. So the best way to find a paper is to go to something called Google Scholar. Google has this separate search engine that only searches for research paper. Go there and search for a paper, read and then read it. So reading a paper is like extremely difficult. Research papers are really dense, and I think most researchers do it, like write papers that way to make it more difficult for common people to read papers and understand their work. But yeah, reading a paper is really difficult. And I remember when I used to first try to read papers, I could hardly like read like, one paragraph or like, 10 sentences without feeling like completely burnt out. That's how dense some papers are. So don't worry, don't give up. It's common. Like it's like completely normal to feel that way. But I want to instill in you this